talk to you guys a bit. The first two sections we did involved momentum and impulse, and they're all lumped in together with this work and energy stuff because there's this idea of conservation. In that case, it was conservation of momentum before and after. And in this case, it's energy. And, well, we're going to talk about this, and it's different than momentum, anyways, but it's conserved as well in certain situations, or in all situations. Anyways, first of all, what do you guys know about energy? What is it measured in the metric system? What's that? Say it out loud. What? Say it out loud. I think you, what'd you say? No, it is not a vector, actually. Energy is not a vector. Okay. Unit. What's that? No, kilojoules. Joules and kilojoules. Yeah. Kelvin is a temperature measure. So there we go. And it's somewhat proportional to the increases in temperature are proportional to kinetic energy of molecules and stuff like this. Anyways, so there's a relation to temperature. But work and energy. Now, work is a type of energy that we're going to multiply or calculate and stuff. Work is force times displacement. And it's important that I say displacement, not necessarily distance. So, it's a vector cross product. And I won't get into what cross product really means here. As long as you just take care of it. In university, if you choose to take engineering or physics for physics majors, you'll understand cross products better. Work, W, we use that. That one makes sense. And you understand force and displacement. I'm going to just pause this for a second. Okay, back at her. So work is a scalar quantity, meaning joules do not have a direction. Okay? And joules is really, we can think of it as a Newton meter, or if you break it down even more, kilogram meters squared over seconds squared, but a Newton meter. And it's easy to think of that, but these are, a joule is proportional to the unit that you use food energy. What is food energy usually measured in? You know this because you count them sometimes. Calories, right? That's measuring the same thing. It's energy. And generally, food calories can be determined if you actually burnt a piece of popcorn or whatever, butter, whatever, and how much energy you get out of that, that's it. So that's potentially what you could get out of eating a piece of popcorn, the calories. Well, not too many, let me just see here, I put that in the back. Not too many things give you the food energy in joules or kilojoules, but they sometimes do. I'm going to just take a look here. This wrapper here. Strictly calories, yeah. It's not too often, especially because most of our stuff is based on American things. I'll just take it through the trash here. Yeah, odd time you get something that gives you also kilojoules and stuff, but this is just calories. Okay. The multiplier is 4.184. I think that's off the top of my head. Translate back and forth between joules. Stick to calories, though, if you're talking about food. Okay. The applied force and displacement have to be in the same direction if work is done. Okay? Now, here's an example of a question where work isn't done. But there's energy spent, maybe, but it doesn't work. Work is force times displacement. It has to be in the same direction. Force pushing. If you are, here's one. Okay, you park on a driveway that is, and I'm going to just draw it. Put it in page that all. You don't have to copy this down. Let's say you're parked on an inclined driveway. There's your vehicle. Anyways. and you got a, say, 1,000 kilograms. And this is a 4-meter driveway on an incline. But it's parked and the brakes are on, it's not skid. How much work is being done to this vehicle? Not the work. I said work. Yes. Is there any displacement? So, no work being done. First of all. Then I say that it has to be done in the same direction. The displacement has to be in the same direction as the force. Yeah. So 1 kilogram. We know the weight force is going to be mg. So the force of gravity is 9.8. Normal. Okay. This is understood. Right now it's not moving, so no work being done, right? I'm pulling it. With a 5-Newton force over a distance of 2 meters or something like that. There is work being done. If I'm pulling the displacement is 2 meters, I just say 5 times 2 is 10. Does that make sense? But the blue has nothing, you would not use the 9.8 newtons as part of that. That's not in the same direction. If I'm lifting that box, I actually have a 1 kilogram mass right there. If I lift 1 kilogram against gravity for 1 meter, how much work did I just do? From here, 1 kilogram. So what force am I pushing against? Yeah. So I'm pushing up with 9.8 force over times 1 meter. Yeah, okay, you get the idea, right? Does that make sense? That's what I use. If I'm going sideways, no. But if I'm lifting against the weight, that's the force I'm applying. So, okay, I'm going to get rid of this page. Clear page, delete. Okay. They have to be in the same direction of working. Well, let's take a look at this. It's going to involve some trick, but it's not as crazy. You pull a cart with a rope at an angle of 60 degrees to the horizontal. How much work is done? It requires 255 newtons of force on the rope, and it is pulled for 30 meters. Okay, so you can imagine this. Maybe you can't count. I'll draw it. You'll draw it too. There's my ground. I didn't give the mass. We don't need it. I didn't really draw that looking like 60 degrees, but whatever. So I've got a string maybe. I'm pulling it. 255 meters. But the motion 30 meters. The work being done is only the sideways, the horizontal component of the force. You guys following on that? The other work is kind of wasted. I think you realize this too. If I was to pull with 255 newtons, but straight, if I crouch down and pull it this way, right? It will probably be going faster than if you're pulling up at the same time. Oh, I mean, that's kind of wasted force. We have to figure out the component that's in the x-axis, okay? So the force in the x direction, because that matches the displacement. Yes, well, you know this. We know how to use triangles. It's 255. And it's the cosine adjacent. So we're doing this. I didn't draw the triangle in, but I think it's this. Imagine it. Green triangle. And then I'd use a calculator. I haven't figured out. Close to 60 is half. So that's the part that's actually applied to doing work to the object, moving. So to multiply the work, this is 127.5. I know I have an extra significant. And the 30 meters, the same direction. Newton times a meter is joules. So 3825, but I'm going to round that. 3830. That is 3 significant. That's right. You have to break it down to what's in what direction. We'll pause. Got a lot of textbook questions we'll take a look at. We'll do the first 5 on. Okay, there's an example on page 261. Work and energy, a hockey puck sliding across ice. Player exerts a constant force, 4.5 newtons, over a distance of 0.15 meters. How much work does the player do on the puck? What's the change in the puck's energy work? So I think we understand from this diagram what's going on there. It's not a true free body diagram. Oh, crap. Back to this. Okay. There we are. Anyways, we got a mass, force, and a distance, horizontal. Using that, that's just a simple multiplication. Okay? Don't worry about this work energy theorem yet, the kinetic energy. We'll talk about it now. I separated it. Now, I think I asked you to do from 261, 3A and B, right? Okay. Yeah. How much work does the climber do on the backpack? So that's climbing straight up. It's against gravity. How much are you lifting the backpack? You know, and if the climber weighs, how much? You can break it down to not just the backpack, but how much lifting your body as well as the backpack. So you'd add in your own mass to that. And then the other question, 5, 6, and 8, page 262. Let me just double check here. People lift a heavy box a distance of 15 meters. They use ropes, one of which makes an angle, so you're going to have to use sines and cosines. How much work do they do? You're going to break it down. 6. And it's using a set of stairs, just as we discussed. Okay, that one should be 5, 6, and 8. Oh, the bicycle, we got a diagram there too. That'll involve the cosines and sines. Let's try those problems. Those shouldn't take too long. We'll see from there, okay?